Hi guys, in this video you're going to learn how we can use correlations and scatter plots to describe different things about the relationship between two variables. By the end of the video you'll know what we're talking about when we say we want to describe the direction, the form, the strength of a relationship, and how we would determine whether it's significant. So like we said in the last video, a correlation measures and describes the relationship between two variables using two variables that are measured in a more continuous way. And we can describe that relationship in three different ways. We can talk about the direction of the relationship, whether it's positive or negative. We can talk about the form or the shape of the relationship, in particular, whether it's linear or nonlinear. And we can talk about how consistent or how strong that relationship is. How close to the diagonal, if we put a line between all of our data, how close to the diagonal all of those data points fall. So let's talk about those three ways now in more detail. First, the direction of the relationship. And you probably have learned this in other classes. Maybe this goes back to your high school days. This is about whether the correlation is positive or negative, or maybe there's no relationship. So what does it mean to have a positive correlation? What does it mean to have a negative correlation? Well, a positive relationship simply means that two variables change in the same direction. The diagonal line goes up. As one variable increases, the other variable increases. Death rate due to COVID increases as age increases. And a positive relationship could also go in the other way. As one variable decreases, the other one decreases too. So death rate due to COVID can decrease as age decreases. This altogether shows a positive relationship. Both variables are moving in the same direction. A negative relationship happens when two variables move in opposite directions. So the diagonal line goes down. As one variable increases, the other variable decreases. An example of this might be that recovery rate due to COVID-19 decreases as age increases. So the point with a negative relationship is that as one goes up, the other goes down. Or we can say that maybe that there's no relationship between our two variables, that change in one variable is not related at all to change in the other variable. An example of this might be that recovery rate due to COVID has no relationship with how tall you are. So remember, a negative correlation is not bad. It's not a bad thing to have a negative correlation. It's just talking about the way that those two variables are moving around. It just means that the variables are moving in opposite directions. And the sign of the correlation might have a lot to do with how we're measuring those variables. So there's two examples here. You might find that there's a positive correlation between the number of hours you study for the midterm and the number of questions you answer correctly. But similarly, there could be a negative correlation between the number of hours you spent studying for the midterm and the number of errors you make on the midterm. So a negative correlation is not bad. It just means that as one increases, the other variable decreases and vice versa. So we can talk about whether the relationship is positive or negative, or there's no relationship. We can also talk about the shape of the relationship. And in particular, what we're looking for is whether the relationship is linear or if it has some other kind of shape. And often it will be a U shape or an inverted U. So in a linear relationship, it means that the data shows a consistent relationship. All the dots in the scatter plot all tend to cluster around a straight line. And if this relationship is positive, it means that each time the variable x increases by 1 point, the variable y will increase by 1 point. So we've got this relationship that's consistent, and we can predict it. So to evaluate whether, so usually we look to see whether the relationship is linear, and the statistical test that we use to evaluate whether that relationship is linear and whether it's significant is the Pearson correlation. So it describes and measures linear relationships when both variables use those numeric scores using interval or ratio scales. And what we get from this is what's called an R value. We usually write it as a small r. And this basically a statistical test that looks at the variance among both of the variables, looking to see how much each person's score varies from the average of everybody. And it looks at both of the variance for both of the variables to look to see how consistent it is. Other kind of relationships that are non-linear use other kind of metrics and statistics. So this is what I'm talking about when I'm talking about linear versus nonlinear. So on the left, you can see that it falls along a straight line. If we increase, we move up by 1 point on the x-axis and move up by 1 point on the y-axis, and we do that this is consistent, that this pattern is consistent throughout all of our data. Versus over here on the other side, we see a non-linear relationship. This is more of a inverted U-shaped relationship. So there's not a consistent pattern with how much one increases doesn't tell us about how much the other one is going to increase. You may remember that we talked about this kind of relationship when we talked about the law of large numbers. And we said that increasing our sample size increases the extent to which our data represents the target population that we're interested in measuring. And we said that increasing the sample size gives us better data, but with diminishing returns. At some point, increasing our sample size doesn't have the same effect. This would be an example of a nonlinear relationship. So when all the data points are pretty close along a straight line, we've got a linear relationship. And that's what we're going to be talking about mostly when we talk about correlations. You may notice in this plot that all of the data points are pretty close to the diagonal. We don't have any dots that are, way over here or way over here. This suggests a strong relationship. And that is the next way that we can describe the relationship between two variables. We can talk about how strong the relationship, which is another way of saying how consistent is that relationship. And we do that by looking at the number, that R value, and whether it gives us a number between, it says 0 and 1, but actually that should be -1 to 1 because it could be positive or negative. So in this picture, all of the dots fall along this line. This line is moving up and to the right. It's a positive relationship, and we would probably get an R value from here that is pretty large and close to 1. So the R value tells us how strong this relationship is. As the R value gets closer to 1, this tells us that there's probably a strong positive relationship. If it's 1 exactly, that would be a perfect correlation. This is an example of a strong positive correlation. It's probably about 0.09 or so. Here, we're over here right in the middle, we have an R value close to 0, which means that there's no relationship. So that means that increasing one variable doesn't tell us anything about how that other variable is going to increase. It means that there is no relationship really between those two variables. Scores on your midterm are probably not going to be related to how tall you are. There's going to be some people who are tall and score poorly on the midterm, and some people who are tall and score really well on the midterm. We have no relationship. Then negative relationships, again, are moving down. And the closer those dots fall to the diagonal, the larger our R value would be. And this suggests that the relationship is strong, a strong negative relationship. And if those dots fall exactly on the line, then that would be a perfect correlation. So here are some more data. I gave a link down at the bottom from where I got this, showing different kinds of relationships and data and what the strength of the relationship would look like and the direction of it, whether it's positive or negative. So here, down here, this would be an example of a very strong negative correlation because all the dots are clustering close to the line and it's going down. This is an example of a pretty strong positive correlation. This line is moving up. As one variable increases, the other one increases, and all the dots are pretty consistent. As those dots spread further apart, the relationship gets closer to 0, and it suggests that that relationship isn't very strong and there may be other factors that are at play. So here's a great chance for you to review, take a look at these 4 plots and see if you can answer this on your own. Which of these show a positive relationship, a negative relationship, or no relationship? And what do you think the R values would be? Would they be closer to 1, closer to -1, or closer to 0? Why don't you see if you can answer these questions, and the answers are down at the bottom of the slide. If you go to Sakai, you'll find these lecture PowerPoints and you can check your answers to see if you're right. So how do we interpret the strength of the correlation? Well, we can look to see whether the dots fall on the line. We can look to see how big that R value is. Anything bigger than 0.5 is usually considered a strong relationship. If you're actually doing, let's say for your honors thesis, a correlational design, and you find that there is a relationship of like 0.6 between two variables, you'd get really excited because this suggests that there's a strong relationship. And in fact, if you square that R value, so you go 0.5 squared, this would give you another term. It's called the coefficient of determination. And this tells us how much of the variance in one variable can be explained by variance in the other variable. So if we've got a strong correlation of, let's say, 0.5, our R squared value would be 0.25, and that means 25% of the variance in one variable can be explained by that other variable. So let's say we were interested in the relationship between the amount of time you spent studying for your midterm and what your midterm scores were. If we found a relationship of 0.5, that would mean that 25% of the variance in how well you do in the midterm could be explained by how long you study for. That means a quarter, we can predict a quarter, 25% of, with like a predictability confidence value of 25%, that if we know how long somebody studies for their midterm, we can predict what their midterm scores would be. So we would also want to run some stats. We'd get our Pearson correlational value. We'd also take into consideration how many participants we had in our whole sample, and this would tell us whether that relationship is significant or not. It tends to be the larger the R value, the more likely that relationship is significant. So here's one more question for you to review, and we'll talk about it at our next Teams meeting. Why don't you see if all of this made sense to you, and see if you can draw a scatter plot that would show the following correlations: negative 0.8, positive 0.3, or positive 0.7. Think about what direction do each of these relationships go, and how clustered around a line those dots would fall, and how would you describe the strength of these relationships? Would you consider them to be strong, moderate, or weak? We'll talk about it at our next Teams meeting. So to summarize, a correlation research involves two sets of measurements for each individual. Our goal is to describe a relationship between those two variables, and we can talk about the nature of that relationship as well. We can talk about whether it's positive or negative, or if there's no relationship, whether it's linear or nonlinear, and whether that relationship is strong, moderate, or weak. And then finally, by doing some statistics, we can really say whether that relationship is meaningful or not. Thanks so much for listening, and we'll see you in the next video.